Picture a cosmic dance so rare, it defies everything we know about star formation. 6 suns, locked in an intricate gravitational embrace, spinning through the void in patterns that baffle even the most brilliant astronomers. This isn't science fiction, it's the reality of sextuple star systems, some of the strangest and most mysterious structures in our universe. Out of the hundreds of billions of stars in our galaxy, only a handful of these 6-star configurations have ever been found, each one rewriting the rules of astrophysics as we know them. These systems aren't just random gatherings of stars, they're precision cosmic machines, with multiple binary pairs orbiting each other in delicate, often chaotic harmony. Their existence challenges our understanding of how stars are born, how they survive, and what happens when gravity plays by its own rules, and the discoveries we've made about them. They're even weirder than you could imagine, from planets trapped in a never-ending sunrise to stars that steal each other's energy like cosmic vampires. These systems are packed with secrets that stretch the limits of what we thought possible. So buckle up, because we're about to dive into 25 of the strangest, most mind-bending discoveries ever made about sextuple star systems, each one more astonishing than the last. By the end of this journey, you'll never look at the night sky the same way again. Now, let's turn our attention to the trailblazer of these cosmic oddities, the first sextuple star system ever confirmed. Nestled within the constellation Eridanus, roughly 1,900 light-years from Earth, lies TUSE 7037-89-1. This system isn't just a random cluster of stars, it's a meticulously organized celestial family, with 3 pairs of binary stars orbiting one another in a dizzying gravitational ballet. What makes TUSE 7037-89-1 so extraordinary is its hierarchical structure. Imagine a cosmic matryoshka doll. The 2 innermost stars orbit each other in a tight embrace, completing a full dance in just 1.5 days. Around them, a second binary pair whirls at a wider distance, taking about 8 years to complete their orbit. And encircling all 4 stars is a third binary duo, moving at an even more leisurely pace. Their orbital dance spans several thousand years. This layered arrangement defies traditional models of star formation, which struggle to explain how 6 stars could emerge so close together without tearing each other apart. Equally baffling is the system's sheer stability. Despite the chaotic gravitational forces at play, these stars have maintained their delicate balance for millions of years. Astronomers suspect that the vast distances between each binary pair act as a buffer, preventing catastrophic collisions. But here's the twist: the stars in TUSE 7037-89-1 aren't identical twins. Some are hotter and more massive, while others are cooler and smaller, a mismatch that challenges the idea that stars in such systems should form from the same primordial cloud. This discovery didn't just add a new entry to the catalogue of multiple star systems, it rewrote the playbook. Before TUSE 7037-89-1, scientists doubted whether sextuple systems could even exist. Now they're forced to reconsider how gravity sculpts stellar families, and whether our universe harbors even more of these intricate cosmic puzzles. And as we'll soon see, this was just the first of many revelations that would turn our understanding of the stars upside down. Moving beyond the trailblazing discovery of TUSE 7037-89-1, let's shine a light on another cosmic marvel, a sextuple star system where the stars don't just orbit but put on a dazzling light show. In the constellation of Leo, astronomers have identified a system where 2 of its binary pairs are eclipsing binaries, a rare phenomenon that turns these stars into celestial lighthouses blinking in perfect rhythm. Here's how it works. When one star in a binary pair passes in front of its companion from our vantage point, it blocks some or all of its light, causing the system's brightness to dip. In this sextuple setup, two separate pairs undergo these eclipses at different intervals, creating a complex pattern of flickers that astronomers can decode like a cosmic Morse code. These brightness fluctuations aren't just pretty to observe, they're golden opportunities for science. By meticulously tracking the timing and depth of each dimming event, researchers can calculate the stars' sizes, masses, and even the precise distances between them with astonishing accuracy. It's like weighing celestial objects using nothing but shadows and math. What makes this system particularly fascinating is the sheer scale of its eclipses. In one binary pair, the stars are so close together that they nearly graze each other's surfaces, causing deep, dramatic dips in brightness. The other eclipsing pair, meanwhile, has a wider orbit, producing gentler, more gradual dimming. This contrast allows scientists to study two very different stages of stellar interaction within the same system. The data reveals everything from the stars' temperatures to their shapes. Yes, stars in tight orbits often stretch into egg-like forms due to gravitational tugging. But the real kicker, these eclipsing binaries also help astronomers map the system's three-dimensional architecture. By combining eclipse data with measurements of the star's Doppler shifts, tiny changes in their light caused by orbital motion, scientists can reconstruct the exact angles at which these pairs orbit each other. This precision is crucial for understanding how sextuple systems maintain stability amid such gravitational complexity. While most multiple star systems hide their secrets in the glare of overlapping light, eclipsing binaries essentially hand scientists a cheat sheet. Every flicker, every dip in brightness is a clue to unraveling the mysteries of stellar evolution. And as we'll see next, these systems aren't just about gravity and light, they can also defy time itself. Now, let's journey to a sextuple star system that throws a cosmic curveball at everything we thought we knew about stellar siblings. Imagine a family where some members are toddlers while others are grandparents. That's exactly what astronomers found in a bizarre system where the stars have ages differing by millions of years. This isn't just a minor discrepancy. It's a full-blown rebellion against the long-held belief that stars in multiple systems form together from the same collapsing gas cloud. At the heart of this mystery lies stellar metallicity, the chemical fingerprints locked in a star's light. Younger stars typically boast heavier elements forged by previous generations, while older stars are more pristine, with lighter elements dominating their composition. In this system, spectroscopic analysis revealed some stars were metal-rich, signaling youth, while others were metal-poor, hinting at advanced age, the gap between them. A staggering tens of millions of years. It's like finding a medieval castle next to a skyscraper. So how did this cosmic age gap happen? One leading theory suggests stellar capture, a game of gravitational tag where a wandering star or even an entire binary pair got snatched by the system's pull. Picture this: a young, dynamic star cluster drifts too close, and boom, the system's gravity yanks a few newcomers into its dance. Alternatively, chaotic mergers could be to blame. If two older stars collided and merged, their fiery rebirth might disguise them as younger stars, creating a false age spread. The implications are profound. If capture is the answer, it means sextuple systems might be cosmic melting pots, assembling stars from different eras like a celestial scrapbook. This challenges the idea that these systems are born in monolithic, single-event collapses. Even more intriguing, it raises questions about stability. Stars with different masses and ages exert varying gravitational influences, potentially destabilizing orbits over time. Yet here they are, coexisting, a testament to the delicate balance of cosmic forces. What's next for researchers? Pinpointing the system's velocity could reveal if it's moving through a dense star-forming region, increasing capture odds. Meanwhile, simulations of stellar mergers might show whether the age gap is an illusion or a true anomaly. Either way, this system forces us to rewrite the rules of stellar families, proving that in the cosmos, sometimes the most dysfunctional arrangements are the most enlightening. And speaking of cosmic surprises, our next discovery takes us to a system where not just stars, but planets defy the odds, orbiting amid the gravitational chaos of six suns. But here's something that truly bends the rules of cosmic possibility: a planet thriving in the gravitational storm of a sextuple star system. If you thought finding a planet around one sun was impressive, imagine a world where six stars dominate the sky. This isn't science fiction. Astronomers have discovered a planet locked in a delicate dance with one binary pair within a six-star chaos, defying every expectation of how and where planets can form. Surviving in such a system is like balancing on a cosmic tightrope. The gravitational tugs from six stars should, in theory, tear any forming planet apart or send it hurtling into space. Yet this planet persists, orbiting its host stars at just the right distance, close enough to avoid being snatched away by other stellar siblings, but far enough to escape destructive tidal forces. Scientists believe its stability hinges on a combination of factors: a wide orbit that minimizes gravitational interference, and the fact that the other four stars in the system are positioned far enough away to act more like distant watchers than disruptive bullies. Now picture the view from this planet's surface. With six suns, daylight would be a shifting spectacle. Some stars might appear as brilliant orbs, while others could resemble dazzling points of light, depending on their distance and luminosity. There could be moments when multiple stars align, casting overlapping shadows, or times when one star eclipses another, creating dramatic celestial performances. And if the planet has an atmosphere, sunsets might paint the sky in surreal hues, with light refracting through layers of gases stirred by the competing gravitational pulls. The discovery challenges our understanding of planet formation. Traditionally, planets are born in the calm outskirts of protoplanetary disks around single stars. But here, material must have coalesced despite the gravitational noise of six stars, a testament to nature's resilience. One theory suggests the planet formed around one binary pair before the system's other stars joined the party, allowing it to settle into a stable orbit early on. Alternatively, it might be a captured rogue planet snared by the system's gravity during a close encounter. What's next for this extraordinary world? Researchers are racing to model its long-term stability. Simulations suggest that while it survives now, subtle changes in the star's orbits could one day send it spiraling away, or worse, into a collision course. Meanwhile, astronomers are scanning other sextuple systems for similar planets, wondering if this discovery is a fluke or a sign that we've underestimated the cosmos's creativity. And just when you think it can't get any stranger, our next revelation takes us to a system where the stars aren't just dancing there on a collision path, destined for a cataclysmic crash. Now, let's turn our attention to a system where the stars aren't just dancing there, headed for a cosmic smash-up. Imagine a sextuple star system so chaotic that its stellar members are destined to crash into one another, not in millions of years, but within a time frame astronomers could actually witness. This isn't just theoretical. Scientists have pinpointed a system where gravitational tugs have thrown stars into wildly unstable orbits, setting the stage for inevitable, violent collisions. What makes these orbits so unpredictable? Normally, multi-star systems settle into stable configurations with gravitational forces balancing out over time. But in this particular system, the stars are locked in a gravitational tug-of-war so intense that their paths keep shifting. Some swing too close to their siblings, others get flung outward only to snap back like cosmic rubber bands. Over time, these chaotic interactions sap energy from their orbits, pulling them closer together until a collision becomes unavoidable. Researchers estimate that within the next few 100,000 years, at least two of these stars will merge in a spectacular explosion of light, heat, and gravitational waves. Speaking of gravitational waves, this is where things get even more fascinating. When massive objects like stars collide, they send ripples through the fabric of spacetime itself, disturbances we can detect with instruments like LIGO and Virgo. A collision in a sextuple system wouldn't just produce one gravitational wave signal, it could trigger a cascade of them, as the remaining stars reel from the aftermath, potentially leading to even more collisions. This would give scientists an unprecedented front-row seat to study how such chaotic events reshape star systems in real time. The cosmic fireworks wouldn't end there. A stellar collision would unleash an enormous burst of energy, possibly creating a superluminous supernova or even forming a new, more massive star from the wreckage. If one of the colliding stars is already a white dwarf or neutron star, the explosion could produce rare elements like gold or platinum, scattering them into space. The remaining stars in the system might then be left orbiting this newly formed object, adding yet another layer of complexity to an already bewildering arrangement. But here's the real kicker: this system isn't just a celestial oddity. It's a living laboratory for understanding how gravity operates under extreme conditions. By observing these stars inching toward disaster, scientists can test theories about orbital dynamics that apply everywhere, from black hole mergers to the formation of planetary systems. It's a reminder that even in the vast stillness of space, chaos and destruction can pave the way for new discoveries. And as if this system couldn't get any more mysterious, our next revelation takes us to one where an invisible presence seems to be pulling the strings, a dark object lurking among the stars. Now let's venture into the shadows of a sextuple star system where something unseen wields incredible power. Picture this: a cosmic family of 6 stars, 5 gleaming brightly, but the 6th. It's utterly invisible, a ghostly presence revealed only by its gravitational grip on the others. This isn't just an empty spot in space. It's a dark object, either a black hole or a neutron star, lurking silently and bending the orbits of its stellar siblings like an unseen puppeteer. How do we even know it's there? The answer lies in the strange behavior of the visible stars. Their paths don't follow the usual rules of gravity as we understand them. Instead, they wobble, speed up, or slow down in ways that can't be explained by the pull of the stars we can see. It's as if an invisible hand is nudging them, and that hand belongs to an object so dense not even light can escape it. Astronomers call this phenomenon dynamical evidence, the universe's way of hinting at hidden masses through the motion of the objects they influence. The dark object's presence isn't just a curiosity, it's a game changer for the entire system. Imagine a spinning top suddenly yanked by an unseen thread. That's what happens here. The invisible body's gravity warps the orbits of the other stars, stretching some into elongated ellipses, while others are forced into tighter, faster paths. If it's a black hole, its pull is so intense that nearby stars might be stripped of their outer layers, feeding a silent, insatiable hunger. If it's a neutron star, its rapid rotation could be lashing the system with deadly beams of radiation, invisible to our eyes but detectable by telescopes tuned to X-rays or radio waves. What's truly mind-bending is how this dark object got there in the first place. Did it form alongside its stellar siblings, only to collapse into darkness while they stayed bright? Or was it captured by the system later, a wanderer pulled into this intricate dance? Either scenario would leave clues in the orbits of the other stars. For instance, if the orbits are wildly misaligned, it might suggest a violent past, perhaps a close encounter that flung the original stars into chaos before this dark intruder settled in. The implications stretch far beyond this one system. If black holes or neutron stars can hide in plain sight within sextuple systems, how many others are out there, unseen but shaping the cosmos around them? It's a humbling reminder that what we observe is only a fraction of what exists. And as we piece together these hidden narratives, we're not just solving a celestial mystery, we're rewriting the rules of how star systems live, evolve, and sometimes hide their darkest secrets. Speaking of secrets, our next discovery takes us to a system where the stars themselves seem to break the rules of chemistry, defying everything we know about how stars should behave. Now, let's turn our attention to a sextuple star system where the stars themselves seem to be breaking the cosmic rulebook, specifically the rules of stellar chemistry. In this peculiar family of 6 stars, some members are loaded with heavy metals like iron, gold, and uranium in amounts that make no sense based on our current understanding of how stars form. You'd expect stars born together to share similar ingredients, like siblings raised in the same household. But here, some stars are metal-rich while others are oddly metal-poor, as if they've been seasoned with entirely different cosmic spices. So why does this matter? In astronomy, a star's metallicity, the amount of elements heavier than hydrogen and helium it contains, is like a birth certificate. It tells us where and when the star formed because the universe started with almost no heavy metals. Over time, generations of stars fused lighter elements into heavier ones, scattering them into space when they died. Younger stars inherit this enriched material, so higher metallicity usually means a later birth. But in this system, that logic falls apart. Some stars are packed with metals, suggesting they're young, while others are metal-poor, as if they're ancient relics. It's like finding a medieval knight sharing a dinner table with a smartphone-toting teenager. One possible explanation is interstellar pollution, a dramatic way of saying these stars might have ingested metal-rich material later in life. Imagine a star passing through a cloud of cosmic debris left behind by a supernova, gobbling up heavy elements like a whale filtering plankton. But here's the twist: in a sextuple system, that pollution would likely affect all the stars equally, yet we see stark differences between them. That leaves us with an even wilder possibility. Some of these stars might not have formed here at all. They could be intergalactic immigrants captured from another galaxy where chemical enrichment happened differently. Another theory points to exotic origins, like a rare class of stars called blue stragglers. These are stars that appear younger and more metal-rich than their neighbors because they've cannibalized another star, stealing its material in a violent merger. If one of these stars crashed into the system later, it could explain the uneven metallicity. Or perhaps the system's chaotic gravitational dances dredged up heavy elements from deep within some stars, splattering their siblings with unexpected metallic paint. Whatever the cause, this metallicity mystery forces us to rethink how stars evolve in crowded systems. It's not just about where they're born, but what happens to them over billions of years: collisions, theft, or even kidnappings from other corners of the cosmos. And if stars can defy chemistry this boldly in sextuple systems, what other cosmic rulebooks are we holding upside down? Up next, we explore a system where the stars aren't just breaking rules, they're creating art, painting the cosmos with the glow of a nebula. Now, let's step into a celestial gallery where the stars themselves are the artists, painting the void with swirls of glowing gas. This sextuple system doesn't just float in darkness, it's cocooned within a nebula, a vast cloud where newborn stars sculpt their surroundings into breathtaking shapes. Imagine 6 brilliant siblings, each blasting out fierce stellar winds, their radiation carving cavities in the nebula like sculptors chipping away at marble. The result, a cosmic masterpiece where tendrils of ionized gas curl around the stars in luminous ribbons, lit up in hues of pink, blue, and gold. Why does this nebula matter? It's not just a pretty backdrop. This glowing cradle is a stellar workshop where the environment actively shapes the star's fates. The nebula's dense gas acts like a cosmic brake, slowing the star's rotation over time. Think of it as stellar spin class, where friction with the nebula's material keeps these suns from whirling out of control. But there's a catch. That same gas can also fuel dramatic growth spurts. As the stars move through the nebula, they hoard material, bulking up like athletes carbo loading before a race. This could explain why some stars in the system appear more massive than stellar formation models predict. The nebula's radiation also plays puppeteer with the star's planets, if any dare to form in this chaotic environment. Intense ultraviolet light from the hottest stars strips away the outer layers of gas giants, leaving behind scorched cores. Meanwhile, the pressure from stellar winds hurls leftover dust and gas into dense rings which might one day coalesce into new worlds. It's a planetary construction zone with 6 foremen, each blasting conflicting orders into the void. But the most mesmerizing effect is time-lapse art. Over millennia, the stars' combined energies etch ever-changing patterns into the nebula. One binary pair might sculpt a towering pillar, while another duo's radiation blows it apart like sand in a hurricane. This constant remodeling offers astronomers a rare chance to study real-time stellar feedback, how stars influence their birth clouds and vice versa. It's like watching a potter reshape clay while the wheel never stops spinning. As we marvel at this interplay, remember, most stars form in such nebulous nurseries, but few get to grow up surrounded by so many siblings. The sheer gravitational pull of 6 stars churns the nebula into a turbulent soup, accelerating chemical mixing and sparking reactions that might not occur in calmer regions. Some theorists even suggest these conditions could brew exotic molecules, the cosmic equivalent of a Michelin star kitchen pushing culinary boundaries. What's certain is that this system challenges the idea of stellar solitude. Here, stars don't just shine, they collaborate, compete, and create, leaving their mark on the canvas of space. And as the nebula eventually disperses, it will carry the fingerprints of this extraordinary family across the galaxy. Next, we encounter a system where the stars don't just move together. They rebel, with some orbiting backward in a celestial game of defiance. Now, let's turn our attention to a cosmic oddity that defies the usual rules of celestial motion. A sextuple star system where some stars orbit backward, like rebellious dancers spinning against the flow. This isn't just a quirk. It's a full-blown astrophysical mystery that challenges our understanding of how star systems form and evolve. In most multi-star systems, siblings move in harmony, their orbits aligned like planets circling the sun in the same flat plane. But here, at least one pair of stars flips the script, tracing a retrograde path orbiting in the opposite direction of the others. Imagine a clock where most hands turn clockwise, but one insists on going counterclockwise. That's the kind of chaos astronomers are grappling with in this system. So how does this happen? One leading theory involves a violent past, a close encounter with another star, or even a rogue black hole. Picture this: millions of years ago, an intruder star might have barreled through the system, its gravitational pull yanking one binary pair into a backward spin like a billiard ball ricocheting off the table's edge. Alternatively, the system could have formed from a turbulent cloud of gas and dust where conflicting rotations left some stars with inverted orbits, like eddies swirling in opposite directions in a rushing river. The implications are staggering. Retrograde orbits can destabilize the entire system over time, leading to dramatic events like stellar collisions or ejections. It's a gravitational tug-of-war where the odd star out might eventually be flung into deep space or dragged into a catastrophic merger. Some simulations even suggest that such chaotic setups could forge hypervelocity stars, runaways hurtling across the galaxy at breakneck speeds, their origins traced back to these orbital rebellions. What's truly mind-bending is how these backward orbits affect any potential planets. In a stable system, planets usually form from a flat, rotating disk aligned with their star's motion. But here, a planet born around a retrograde star would see its sun rise in the west and set in the east, with other stars zooming across the sky in conflicting directions. The gravitational tugs from multiple misaligned orbits would make planetary orbits unstable, likely dooming any worlds to a short, chaotic existence before being ejected or shredded. Astronomers are racing to study this phenomenon because it's vanishingly rare. Most sextuple systems discovered so far have orderly, aligned orbits. This outlier could be the key to understanding how extreme gravitational encounters shape stellar families. And if retrograde orbits are more common than we thought, It might force us to rethink how often stars steal siblings from passing systems or emerge from disordered stellar nurseries. As we marvel at this cosmic defiance, remember it's not just a celestial spectacle. It's a reminder that the universe loves breaking its own rules, leaving us to piece together the how and why. Next, we'll explore a system where stellar drama takes a darker turn, with one star draining the life from another in a cosmic vampiric act. Shifting our gaze to another cosmic spectacle, we encounter a sextuple system where stellar drama takes a deadly turn, a vampire star feasting on its companion. This isn't science fiction. It's a real celestial phenomenon where one star drains the life out of another, growing unnaturally bright while its victim withers away. Picture this: two stars locked in a tight binary embrace, so close that the gravity of the larger star peels away layers of its smaller companion. The stolen gas spirals onto the vampire star's surface, heating up and glowing intensely, while the donor star grows dimmer and more distorted. Over time, this cosmic theft can lead to explosive consequences. One possibility: the vampire star gorges itself until it reaches a critical mass, triggering a cataclysmic supernova. Alternatively, the donor star might be stripped down to its bare core, leaving behind a bizarre stellar remnant like a white dwarf or neutron star. What makes this even wilder is the role of the other four stars in the system. Their gravitational tugs can destabilize the vampire binary, sometimes yanking the stars closer together, accelerating the feeding process, or flinging them apart, cutting off the blood supply. Imagine a chaotic dance where every nearby star influences this deadly relationship. The vampire phenomenon isn't just destructive, it's also a cosmic recycler. The stolen material enriches the predator star with fresh hydrogen, effectively resetting its lifespan. A star that should have aged into a red giant might instead blaze as a blue straggler, appearing younger and hotter than its siblings. Some vampire stars even end their lives as ultra-dense objects like Magnetar's neutron stars with magnetic fields so strong they could wipe data from Earth satellites from thousands of light years away. For astronomers, these systems are gold mines. By studying the vampire's feeding patterns, they can decode the physics of mass transfer, stellar evolution, and even the origins of rare supernova types. And if a supernova does occur in a sextuple system, the shockwaves could ripple through the other stars, altering their orbits or triggering secondary explosions. This isn't just a tale of stellar cannibalism, it's a window into how stars cheat death, rewrite their fates, and sometimes light the fuse on cosmic fireworks. Next, we'll witness a system where gravity plays the ultimate prank, ejecting a star at speeds that defy imagination. Now, let's turn our attention to a sextuple system that's playing a game of cosmic pinball, launching one of its stars into the void at mind-blowing speeds. This is no ordinary stellar escape. We're talking about a hypervelocity star racing through the galaxy so fast it could cross the distance between Earth and the Moon in just under 2 minutes. How does a star even reach such insane velocities? The answer lies in a gravitational slingshot, an extreme celestial maneuver. Picture this: in a sextuple system, the intricate dance of 6 stars creates chaotic gravitational forces. Sometimes, a close encounter between 2 binary pairs can fling a star outward like a stone from a sling. The star steals energy from its siblings' orbits, accelerating to speeds exceeding 1 million miles per hour. In rare cases, a rogue black hole lurking nearby might provide the final kick, sending the star careening into interstellar space. Tracking these runaway stars is like following cosmic breadcrumbs. Astronomers have traced one hypervelocity star's path back to a sextuple system in the constellation Leo, over 5,000 light-years away. Its trajectory suggests it was ejected roughly 2 million years ago, and now it's streaking toward the outer edges of the Milky Way. But here's the twist: its fate depends on speed. If it's fast enough, it could escape our galaxy entirely, drifting alone through the intergalactic void. If not, the Milky Way's gravity might eventually reel it back in, sending it on a colossal elliptical orbit that could take hundreds of millions of years to complete. What's left behind in the sextuple system is just as fascinating. The ejection of a star creates chaos, orbits rearrange, binary pairs tighten or split, and the remaining stars might even get a speed boost from the event. In some cases, the departing star's momentum can trigger a chain reaction, destabilizing the entire system over time. Imagine a game of gravitational dominoes where one star's exit alters the destiny of the rest. For scientists, hypervelocity stars are more than just interstellar speedsters, they're clues. Their paths help map the Milky Way's hidden gravitational landscape, revealing the locations of dark matter and rogue black holes. And for the sextuple system left behind, it's a living lab for studying how stars adapt to violent change. Next up, we'll explore a system where the universe's most precise timekeepers, pulsars, add a rhythmic pulse to the chaos of 6 stars. Shifting our gaze from runaway stars to the universe's most precise timekeepers, let's uncover a sextuple system where chaos meets clockwork precision. Imagine a stellar family where at least one member is a pulsar, a rapidly spinning neutron star that beams radio waves like a cosmic lighthouse with metronomic regularity. These dead stars, born from supernova explosions, are so dense that a single teaspoon of their material would weigh as much as a mountain on Earth. But in a sextuple system, their presence isn't just exotic, it's a game-changer for physics. Take the system PSR J0337+1715, where a pulsar orbits 2 white dwarfs in a gravitational tango so tight it could fit inside our Sun. The pulsar's ticks, arriving every 2.7 milliseconds, are so precise they rival atomic clocks. But here's where Einstein comes in. According to his theory of general relativity, massive objects like stars warp spacetime, altering the flow of time itself. In this system, the pulsar's signals pass through the gravitational fields of its 5 siblings, causing subtle delays. By measuring these delays, astronomers have confirmed Einstein's predictions with unprecedented accuracy. It's like using the pulsar as a stopwatch to weigh the stars around it and map the invisible fabric of spacetime. But the real magic happens when 2 pulsars share the same system. Their mutual gravity emits ripples in spacetime called gravitational waves, another prediction of relativity. In 2003, the discovery of the double pulsar PSR J07373039 provided the first indirect proof of these waves. In a sextuple system, the dance of multiple pulsars could create a symphony of gravitational waves, offering new ways to test if Einstein's equations hold true under extreme conditions. Yet pulsars in such crowded systems face bizarre fates. Some get recycled or spun up to dizzying speeds by stealing material from a companion star. Others might be kicked out of orbit, becoming rogue pulsars. And in rare cases, collisions could create a supermassive neutron star or even a black hole. For astronomers, these systems are natural laboratories for probing the limits of physics, from quantum mechanics to gravity's grandest scales. Now, let's turn to another gravitational oddity, a sextuple system where one binary pair is staging a daring escape. Now, let's witness a cosmic drama where gravity plays the ultimate game of tug-of-war. In the vast dance of sextuple star systems, sometimes a pair of stars decides to go rogue, breaking free from their stellar family in a daring escape. This phenomenon isn't just rare. It's a window into the chaotic forces shaping these complex systems. Take the system HD 5980, where astronomers spotted a binary pair racing away from its 4 siblings at a staggering speed of over 30 kilometers per second. What could fling 2 stars into such a reckless flight? The answer lies in gravitational chaos. In a sextuple system, the interplay of 6 stars creates a volatile environment. Close encounters between pairs can slingshot one binary outward like a celestial catapult, overwhelming the bonds holding them together. It's as if the system itself ejected them for trespassing too close to another pair's territory. But here's the twist. Unlike hypervelocity stars which vanish into the galaxy forever, these runaway binaries might not be gone for good. Some simulations suggest their escape could be temporary. The gravitational pull of the remaining 4 stars might eventually reel them back in, leading to a spectacular reunion or even a collision. Imagine 2 stars, after centuries of exile, crashing back into their siblings with enough force to trigger novas or reshape the entire system's architecture. Yet other theories argue these runaways are one-way travelers. If they gain enough speed, they'll break free entirely, drifting into interstellar space as orphan binaries. These cosmic nomads could eventually stumble into another star system, triggering fresh chaos, or wander alone for billions of years. The fate of HD 5980's rogue pair remains uncertain, but its story highlights a key truth. Sextuple systems aren't just static families. They're dynamic, ever-changing ecosystems where stars are born, ejected, or reshuffled by gravity's whims. This discovery also raises tantalizing questions. Could our own sun have been part of a runaway pair long ago, ejected from a crowded stellar nursery? While we'll never know for sure, these rogue binaries remind us that even in the cosmos, some stars are destined to break the rules. Next, we'll step into a stellar nursery where sextuple systems are born in the densest corners of the galaxy. Now, let's journey to the cosmic cradles where sextuple star systems are forged, stellar nurseries so densely packed. They're like celestial factories churning out stars by the handful. These chaotic, gas-rich environments are where gravity works overtime, weaving intricate families of stars bound together from birth. Take the system star system name, nestled in the heart of the nebula named Nebula. Here, dense clouds of gas and dust collapse under their own weight, fragmenting into multiple cores that ignite into stars. In such crowded nurseries, the sheer density of material increases the odds of multiple stars forming close together. Imagine a crowded room where 6 dancers emerge from the same swirling mist, each born from the same chaotic cradle, yet destined to orbit one another in an elaborate gravitational ballet. What makes these nurseries special is their extreme environment. Unlike quieter regions where single or binary stars dominate, these factories operate under intense pressure. Turbulent gas flows and frequent collisions between young stars can nudge them into tight groupings. Some astronomers compare it to a cosmic game of pinball, where protostars bounce and merge until a stable sextuple system emerges. The Orion Nebula, one of the most famous star factories, has birthed countless binaries and triples, but sextuples that requires conditions even more extreme. The system star system name offers a clue. Its stars share nearly identical ages and chemical compositions, suggesting they formed together in a single, tumultuous event. Yet their orbits are surprisingly stable, hinting at a delicate balance struck early on. Compare this to the trapezium cluster in Orion, where young stars jostle for space, and the difference is clear. Sextuple systems like this one must have either formed in quieter pockets of their nursery or undergone rapid orbital adjustments to avoid tearing themselves apart. But here's the puzzle. If these systems are born in such frenzied environments, why are they so rare? The answer might lie in survival. Most multiple star systems are likely unstable from the start, with gravitational tugs ejecting members until only binaries or triples remain. For a sextuple to endure, it must strike a perfect equilibrium, a cosmic tightrope walk few can manage. This discovery reshapes how we view star formation. It suggests that in the densest corners of the universe, where gas and dust collide with ferocious energy, nature occasionally engineers stellar families of breathtaking complexity. And just like that, we're reminded that the cosmos has a flair for drama, constructing intricate systems where 6 stars can emerge from the same fiery womb, destined to dance together for eternity. Next, we'll encounter a star that defies time itself, a celestial anomaly glowing younger and bluer than its siblings. as if it found a cosmic fountain of youth. Now, let's turn our attention to a cosmic oddity that shouldn't exist, a star that refuses to age gracefully. In the midst of a bustling sextuple system, one star stands out like a rebellious teenager at a family reunion, the blue straggler. This celestial outlier shines brighter, bluer, and seemingly younger than its siblings, defying the rules of stellar evolution. How does a star cheat time in a system where gravity dictates every move? The answer lies in cosmic cannibalism and the chaotic dance of 6 stars. Take the system name, where 5 stars glow with the expected golden hue of middle age, while the 6th burns an intense blue. Blue stragglers aren't just rare, they're cosmic glitches. Normally, stars in a cluster form around the same time and age uniformly. But here, gravitational interactions in sextuple systems create perfect conditions for stellar vampirism. Imagine 2 stars in a tight binary pair. Over time, one star siphons material from its companion, bulking up until it reignites with fresh fuel. The result: a star that looks rejuvenated, basking in borrowed youth while its donor star fades away. In sextuple systems, the chaos amplifies. With so many gravitational players, close encounters between stars become inevitable. A pair might veer too close to another binary, triggering a merger or mass transfer. Some blue stragglers could even be the product of full-on stellar collisions, cosmic car crashes that forge a single, massive star from 2 smaller ones. The system name offers a clue. Its blue straggler orbits unusually close to 2 other stars, as if locked in a tug of war for material. But why does this matter? Blue stragglers are more than just cosmic curiosities, they're windows into stellar survival tactics. In most environments, mergers are rare, yet in sextuple systems, the density and gravitational interplay make these events far more likely. Astronomers suspect these systems might be factories for blue stragglers, churning them out at rates dwarfing those of simpler star clusters. Here's the twist: blue stragglers can destabilize their entire system. Their extra mass alters gravitational balances, potentially flinging sibling stars into new orbits, or even ejecting them entirely. It's a reminder that in the cosmos, even the quest for youth has consequences. As we unravel the secrets of these stellar rebels, we're left to wonder, could the very dynamics that create blue stragglers also spell the end for their sextuple families? Next, we'll encounter a sextuple system so bright you might just spot it with your naked eye, a celestial spectacle hidden in plain sight. Now, let's step away from the telescope for a moment and look up with nothing but our own eyes. Imagine spotting not 1, not 2, but a dazzling sextuple star system without any magnification, a cosmic rarity hiding in plain sight. While most of these complex systems require advanced instruments to observe, there's one exception: the brightest component of the Castor system, a stellar family in the constellation Gemini. To the naked eye, Castor appears as a single, unassuming point of light. But it's actually a staggering 6-star ensemble, with 2 of its binary pairs bright enough to resolve under perfect conditions. Located just 51 light-years away, Castor is one of the closest and most accessible sextuple systems to Earth. On a clear winter night, you can find it by tracing a line from Orion's belt upward to the twin stars of Gemini, Pollux and Castor. While Pollux is slightly brighter, Castor holds the real secret: a gravitational tango of 6 stars locked in an intricate orbital ballet. What makes Castor extraordinary isn't just its visibility, it's its cultural footprint. Ancient civilizations revered this star. The Greeks associated it with one of the mythical twins, while Babylonian astronomers logged its position as early as 2,000 years ago. Even early telescopic observers in the 17th century noted its unusual double nature, though they had no idea of the deeper complexity lurking within. Today, we know Castor's 6 stars are divided into 3 binary pairs, each orbiting a common center of gravity in a hierarchy so precise it defies intuition. Here's the kicker: the two brightest binaries, Castor A and Castor B, are so close they appear as a single star to casual observers. But with keen eyes and a dark sky, some stargazers report barely splitting them apart. The third binary, Castor C, is far dimmer and requires magnification, but the fact that part of this system is naked eye visible is a testament to its brilliance. Why does this matter? Castor challenges the assumption that complex star systems are always faint or distant. It's a reminder that the universe hides its most intricate wonders in the most familiar places. For amateur astronomers, spotting Castor is like uncovering a secret layer of the cosmos, one that's been overhead for millennia, waiting to be noticed. As we marvel at this celestial beacon, we're reminded that sometimes the universe's greatest spectacles don't require technology, just a moment to look up and wonder. Next, we'll venture into a system where the stars aren't just dancing, they're waging a cosmic war, surrounded by the debris of their clashes. But if you think Castor's orderly dance is the rule for sextuple systems, brace yourself, because some of these stellar families are anything but peaceful. Picture this: a cosmic battlefield where stars don't just orbit, they collide, leaving behind a chaotic haze of dust and debris. That's exactly what astronomers found in one particular sextuple system, a place so turbulent it's been dubbed a war zone of the stars. At the heart of this system, gravitational chaos reigns. Unlike the stable hierarchies we've seen elsewhere, here the stars are locked in a relentless tug of war, their orbits so unstable that close encounters are inevitable. Every time two stars swing too close, they unleash violent stellar winds, tearing material from one another and flinging it into space. The result: a vast, glowing shroud of dust and gas that envelops the entire system, a visible scar of their endless skirmishes. What makes this debris field so fascinating is how eerily it resembles the early days of our own solar system. Billions of years ago, before planets took shape, the Sun was surrounded by a similar disk of dust and rock, a chaotic nursery where collisions were the norm. In this sextuple system, that process is happening in real time, but on a far more dramatic scale. Imagine not just one star shaping its surroundings, but six, each stirring the pot with their gravity and radiation. The debris isn't just static, it's a swirling tempest with clumps of material occasionally smashing together, some perhaps even forming planetesimals, the building blocks of future worlds. Here's the twist: while our solar system's disk eventually calmed down, allowing planets to coalesce, this sextuple system's environment is too wild for that. The constant gravitational jostling prevents any large objects from forming peacefully. Instead, the dust is continually stirred up, a testament to the system's unending turmoil. Astronomers compare it to a game of cosmic bumper cars, where every potential planet gets shattered before it can grow. Yet, within this chaos lies a clue to how stars shape their environments. The dust in this system isn't just random rubble, it's rich with heavier elements like silicon and carbon, forged in the hearts of these stars and ejected during their clashes. Over eons, this material might escape entirely, seeding nearby space with the ingredients for new stars and planets. In a way, this violent system is a factory, recycling itself into the cosmos. As we pull back from this dusty battleground, we're left with a humbling thought. Not all stellar families are harmonious. Some are born from conflict, their legacies written in the debris they leave behind. Up next, we'll encounter a system where one of the six stars isn't a star at all, but a strange, dim outcast that defies expectations. Now let's turn our attention to a system where one of the six members isn't pulling its weight, at least not in the way you'd expect. Nestled within this cosmic family is a brown dwarf, often called a failed star. It's not quite a star, not quite a planet, but something in between, and its presence throws the entire system into fascinating disarray. Brown dwarfs are cosmic underachievers, objects massive enough to stir up trouble but too small to ignite the fusion reactions that power true stars. Imagine a body dozens of times heavier than Jupiter, yet it barely glows, emitting only a faint infrared warmth. In this sextuple system, the brown dwarf isn't just a silent observer. It's an active player, warping the delicate gravitational balance around it. Here's how it shakes things up. Normally, stars in a sextuple system follow predictable rhythms, their orbits governed by mutual gravity, but add a brown dwarf and suddenly those rhythms get jagged. Its gravitational pull, though weaker than a true star's, is still strong enough to nudge its siblings off course. Think of it like a dancer who keeps missing the beat, throwing the whole troupe out of sync. Over time, these tiny disruptions compound, subtly altering the paths of nearby stars in ways that defy standard models. Temperature is another casualty of this oddball's presence. Stars in compact multiples often heat each other through radiation, but a brown dwarf barely contributes. Instead, it acts like a cold spot in the system, absorbing warmth without giving much back. Nearby stars may experience unusual cooling effects on their facing sides, creating lopsided temperature distributions that baffle astronomers. In some cases, this could even affect stellar winds or magnetic activity, adding another layer of complexity to an already chaotic environment. But here's the most intriguing twist. Brown dwarfs are notorious for their strong magnetic fields, far more powerful than their faint light suggests. If this one's magnetic field interacts with the plasma winds of its stellar siblings, it could generate bizarre auroras or even radio emissions detectable across interstellar space. Picture invisible energy crackling between these bodies, a hidden dialogue in a language of magnetism and charged particles. What does this mean for the system's future? Unlike the violent collisions we've seen elsewhere, the brown dwarf's influence is slow but relentless. Over millions of years, its gravitational tugs could push one or more stars into unstable orbits, potentially ejecting them entirely. Or it might settle into a quieter role, a dim anchor around which the others adjust. Either way, its presence is a reminder that even the failures in the cosmos can shape destinies. Up next, we'll explore a sextuple system where the stars aren't just bound by gravity. They're united by something far more unexpected, perfectly aligned magnetic fields, creating a celestial circuit unlike anything else in the galaxy. Now let's step into a cosmic phenomenon where gravity isn't the only force shaping the dance of stars. In this sextuple system, the stars share something extraordinary. Their magnetic fields are perfectly aligned, as if choreographed by the universe itself. Imagine 6 stars not just bound by their mutual pull, but linked by invisible lines of magnetic force, creating a vast, interconnected circuit thrumming with energy. Most stars have magnetic fields, but they're usually chaotic, twisting and flipping independently like unruly compass needles. Here, though, something has synchronized them. Picture a cosmic orchestra where every instrument tunes to the same pitch, producing harmonies instead of noise. Astronomers suspect this rare alignment could be the result of a shared past. Perhaps these stars formed from the same primordial cloud, their magnetic fields imprinted with identical orientations from birth. Or it might stem from their tight orbits, with constant close encounters forcing their fields into lockstep over eons. The effects of this magnetic unity are staggering. When stellar wind streams of charged particles flow between these stars, they ride the aligned field lines like highways, creating colossal electric currents. These currents could generate dazzling auroras on any planets lurking in the system, far more intense than our northern lights. Imagine a world where the sky crackles with neon rivers of light, arcing from horizon to horizon, powered by the synchronized pulses of 6 suns. But the surprises don't stop there. Aligned magnetic fields can also act as accelerators, slingshotting particles to near light speeds. If these high-energy particles collide, they might produce bursts of X-rays or gamma rays, turning the system into a natural particle physics lab. Some researchers even speculate that such conditions could foster exotic plasma structures. Think of glowing loops or rings bridging the stars. visible only in specific wavelengths. What's truly puzzling is how such alignment persists without crumbling. Magnetic fields should tangle and decay over time, yet here they endure. One theory suggests the star's rotations have synchronized too, like gears in a clock, keeping their fields locked. Another proposes that an unseen force like a shared disk of charged gas acts as a stabilizer, constantly reinforcing the alignment. This system doesn't just challenge our understanding of magnetism in stars, it hints at broader possibilities. Could aligned fields help stabilize other complex systems? Might they influence planet formation or protect worlds from deadly radiation? Every answer leads to new questions, proving once again that the cosmos saves its most mesmerizing secrets for those who look closely. Coming up, we'll encounter a star that cheated death, a so-called zombie star wandering among its siblings, a ghostly remnant of a catastrophic explosion. How does its presence rewrite the rules for its entire system? Stay tuned. Now let's turn our attention to something even more unsettling, a star that defied death itself. In this sextuple system, one member is a cosmic anomaly, a so-called zombie star that somehow survived the catastrophic explosion of a supernova. Unlike its stellar siblings, this object isn't burning brightly or fusing elements in its core. Instead, it's a ghostly remnant, a bizarre survivor wandering among its family like a specter from a forgotten apocalypse. Supernovas are supposed to be final acts. When massive stars exhaust their fuel, they collapse under their own gravity and detonate with unimaginable force, often leaving behind either a black hole or a dense neutron star. But in this system, the rules were bent. The zombie star is likely the stripped-down core of what was once a much larger star, a bizarre hybrid that somehow endured the blast. Imagine a tree reduced to its roots after a wildfire, still clinging to life while everything around it turned to ash. That's the essence of this stellar oddity, a charred relic refusing to fully die. Its presence sends ripples through the entire system. A supernova releases so much energy that it can fling nearby stars off their orbits like billiard balls struck by a cue. Yet here, the zombie star remains gravitationally bound to its siblings, suggesting the explosion was either asymmetrical or peculiarly gentle. One theory posits that the dying star might have shed much of its mass beforehand, weakening the blast. Another idea is that the complex gravitational dance of the sextuple system somehow cushioned the impact, absorbing the shock like a cosmic buffer. But don't mistake survival for peace. The zombie star is anything but stable. Its very existence warps the dynamics of the system. For one, it's far denser than its living siblings. A teaspoon of its material would weigh billions of tons. This extreme mass distorts the orbits of nearby stars, creating unpredictable wobbles. Some astronomers speculate that over time, these disruptions could fling one or more stars out of the system entirely, turning a sextuple into a quintuple or even a quadruple arrangement. Then there's the radiation. Zombie stars, especially if they're neutron stars, often emit intense beams of X-rays or gamma rays as they spin. Any planets in the system would be periodically bathed in lethal doses of high-energy radiation, sterilizing surfaces and shredding atmospheres. Picture a world where the sky periodically lights up with deadly flares, a grim reminder of the zombies' presence. Perhaps most intriguing is what this star tells us about stellar resilience. Its survival challenges the textbook definition of a supernova, suggesting that some stars might undergo failed or partial explosions. Could there be other zombies lurking in multi-star systems unnoticed until now? And what does that mean for our models of stellar life cycles? As we ponder these questions, remember this: the cosmos loves exceptions. Just when we think we understand the rules, it throws us a curveball like a star that refuses to die. Up next, we'll encounter a system so ancient, its stars might have witnessed the dawn of the Milky Way itself. How have they endured the eons without drifting apart? The answer awaits. Now let's journey back in time to a system so ancient it might have watched the Milky Way take its first breath. Among the countless sextuple star systems scattered across the cosmos, one stands out not for its violence or oddities, but for its astonishing age. This stellar family is older than our galaxy itself, a relic from an era when the universe was still shaping its grand structures. Imagine stars that have burned for over 13 billion years, nearly as old as the cosmos. Most stars from that epoch have long since died, their remnants recycled into new generations. Yet here, 6 stars remain bound together, defying the odds of time and gravity. How did they survive when so many others vanished? The answer lies in their quiet, unassuming nature. These aren't massive, short-lived giants destined for explosive deaths. Instead, they're smaller, cooler stars, red dwarfs and sun-like stars, that burn their fuel slowly, stretching their lifespans across eons. Their longevity isn't the only puzzle. How did a sextuple system stay intact for so long? In a dynamic universe where gravitational interactions constantly scatter stars, maintaining such a complex arrangement for billions of years seems impossible. One theory suggests this system formed in an unusually dense pocket of the early universe, where stars were packed so tightly that their mutual gravity created a stable, long-lasting bond. Picture a group of friends holding hands in a swirling crowd. Their grip keeps them together despite the chaos around them. Another clue comes from their metallic content, or rather, the lack of it. These stars are metal poor, meaning they contain very few elements heavier than hydrogen and helium. That's a signature of ancient stars born before supernovas enriched the cosmos with heavier elements. Their pristine composition acts like a cosmic fingerprint, placing them among the first generation of stars to illuminate the universe. But surviving isn't the same as thriving. Over time, the system has likely lost members to gravitational tugs from passing stars or interstellar clouds. Yet the core 6 endure, their orbits subtly tweaked but never shattered. Some astronomers propose they've spent most of their lives drifting in the Milky Way's quiet outskirts, far from the disruptive forces of the galactic center. It's like living in a secluded village instead of a bustling city, fewer chances for chaos to tear them apart. What's most humbling is the perspective these stars offer. They've witnessed galaxies collide, black holes awaken, and countless stars flare into existence and fade away. If they could speak, they'd tell stories of a universe far stranger than we've imagined. And yet, here they are, silent, steady, and still shining. As we marvel at their endurance, let's turn to another enigma, a star that seems to glitch like a malfunctioning clock. What cosmic forces could cause a star to speed up or slow down without warning? The answer might lie in the gravitational tug of war of its siblings. Now, let's shift our gaze to a star that seems to defy the rules, a celestial rebel whose rhythm is anything but steady. In the intricate dance of a sextuple system, astronomers have spotted a star that behaves like a glitching clock, its rotation speeding up or slowing down without warning. This isn't just a minor hiccup, it's a full-blown cosmic mystery. Stars, much like planets, usually rotate at predictable speeds. Their spin is governed by the conservation of angular momentum, a fundamental law of physics. But in this system, one star bucks the trend. Imagine a figure skater pulling their arms in to spin faster, then suddenly extending them to slow down, except here, there's no skater, just a star seemingly changing its mind mid-twirl. The cause, most likely, the relentless gravitational tugs from its 5 siblings. In a sextuple system, the gravitational forces are a chaotic web, with each star pulling on the others in complex, ever-shifting ways. One hypothesis suggests that these tidal forces could distort the star's shape, transferring energy between its rotation and its orbit, creating these bizarre speed shifts. But the glitches don't stop there. Occasionally, the star's rotation changes so abruptly that it leaves astronomers scratching their heads. Could there be unseen factors at play? Some speculate that magnetic fields, twisted by the star's turbulent interactions, might be braking or accelerating its spin like an invisible hand. Others wonder if the star has a hidden companion, a dense remnant like a neutron star or a black hole, lurking nearby, yanking it off kilter with each pass. This behavior isn't just a curiosity, it's a window into the broader enigmas of stellar physics. Glitching stars challenge our models of how angular momentum works in multi-star systems. They force us to reconsider how energy is exchanged between stars and whether our understanding of tidal forces is complete. Even more intriguing, similar glitches have been spotted in isolated stars, raising the question, are these anomalies more common than we thought? Could sextuple systems, with their extreme gravitational environments, be the cosmic labs where these phenomena are easiest to spot? The implications stretch beyond this one system. If stars can glitch, what does that mean for the stability of planetary orbits around them? Could a sudden slowdown or speed up spell doom for any nearby worlds? And what about the star's internal structure? Could these jolts trigger massive stellar quakes or flares? The more we learn, the clearer it becomes. The universe loves throwing curveballs. As we ponder this star's erratic dance, let's turn to another puzzle, one where the very fabric of a sextuple system seems to defy logic. Could invisible dark matter be pulling the strings? The answer might lie in the ghostly halos that could surround these stellar families. Now, let's venture into one of the most enigmatic possibilities in astronomy, where the unseen might be shaping the cosmos in ways we can barely fathom. Picture a sextuple star system where the stars move as if guided by an invisible hand, their orbits defying expectations unless we account for something we can't even see: dark matter. This particular system has astronomers divided. On one side, there are those who argue that the star's motions are impossible to explain with gravity alone unless there's a massive, invisible halo of dark matter enveloping the system, tugging on the stars like phantom strings. The math seems to support it. When physicists calculate the orbits based solely on the visible stars, the numbers don't add up. The stars behave as if there's extra mass lurking in the shadows, warping their paths in subtle but measurable ways. But not everyone is convinced. Skeptics point to alternative explanations, like observational errors or hidden stellar remnants too dim to detect. Could a stray neutron star or a rogue black hole be masquerading as dark matter? Or perhaps the complex gravitational interactions in a sextuple system are simply more chaotic than our models can predict, creating illusions of missing mass. After all, with 6 stars pulling on one another in a relentless cosmic tug of war, even small miscalculations could throw off our calculations. The debate isn't just academic, it cuts to the heart of one of astrophysics' biggest mysteries. If dark matter truly is at work here, it would be the first time we've detected its influence on such a small, intimate scale. Most evidence for dark matter comes from galaxies or galaxy clusters, where its gravitational effects are unmistakable. But in a single star system, that would be groundbreaking. It could mean dark matter isn't just spread out in vast, diffuse clouds, but might also clump in denser pockets around individual systems. On the other hand, if this turns out to be a case of misapplied physics or overlooked stellar objects, it's a humbling reminder of how much we still don't understand about multi-star dynamics. Either way, this system forces us to question our assumptions. Are we seeing the fingerprints of dark matter, or is the universe playing tricks on us? As we wrestle with these questions, another cosmic oddity awaits, one that challenges the very limits of what we thought was possible in stellar systems. How can a sextuple system exist when the math says it shouldn't? The answer might lie in the delicate balance of celestial forces. Now, let's turn our attention to a cosmic rebel, a sextuple star system that laughs in the face of astrophysical predictions. This isn't just a rare configuration. It's a system that, according to our best mathematical models, should have torn itself apart eons ago. Yet here it is, thriving against all odds, forcing scientists to rewrite the rules of stellar dynamics. The problem lies in something called the dynamical stability limit. In simple terms, this is the point at which a multi-star system becomes too complex for its own good. Imagine trying to balance 6 marbles on a wobbly table, each rolling in its own direction while tugging the others along. Eventually, the chaos would send them flying. That's what theorists expected to happen here. With 6 stars entangled in a gravitational dance, their orbits should have destabilized long ago, ejecting stars or triggering collisions. But somehow, this system has found a way to endure. What makes it even more baffling is the sheer intricacy of its orbits. Most stable multi-star systems arrange themselves in neat hierarchies, like a set of nested Russian dolls with smaller binaries orbiting a central pair. But this sextuple system scoffs at simplicity. Its stars crisscross in ways that defy conventional patterns, weaving a gravitational web so complex that supercomputers struggle to simulate it. Some stars loop around each other in tight spirals, while others trace wide, lazy arcs, all without a single misstep. So how does it survive? One wild theory suggests the stars might be locked in resonant orbits, a celestial rhythm where their gravitational tugs sync up, cancelling out chaos. Think of it like a perfectly timed metronome where each beat balances the next. Another idea is that the system is younger than we think, and its inevitable collapse simply hasn't happened yet. Or perhaps there's an unseen factor, a hidden mass or a delicate arrangement we haven't detected that's acting as a cosmic glue. Whatever the answer, this system is more than a curiosity. It's a stress test for our understanding of gravity itself. If our models can't explain its stability, what else might we be missing about how stars interact? Could there be other impossible systems hiding in plain sight, waiting to upend our theories? As we grapple with these questions, we're reminded that the universe thrives on defying expectations. And just when we think we've unraveled its rules, along comes a sextuple star system that dances to its own tune, one we're still straining to hear. And speaking of cosmic dances, our final discovery takes harmony to another level entirely. Imagine a sextuple system where the stars move in perfect rhythm, like a grand celestial ballet. Now, as we reach the grand finale of our cosmic journey, we encounter a sextuple star system that moves with the grace of a perfectly choreographed dance. Picture this 6 stars, each locked in a delicate gravitational embrace, tracing paths so precise they seem to follow an invisible sheet of music. This isn't just random motion. It's orbital resonance, a rare phenomenon where the stars' orbits sync up in perfect mathematical harmony, like gears in a celestial clock. What makes this system extraordinary is how it defies the chaos we'd expect from such a crowded stellar neighborhood. Normally, when 6 stars share space, their gravitational pulls should lead to erratic movements, collisions, or ejections. But here, the stars have settled into a rhythm so stable it's almost poetic. For every 3 orbits one pair completes, another pair might complete too, their gravitational nudges reinforcing rather than disrupting each other. It's as if the universe itself composed a symphony, with each star playing its part flawlessly. Scientists call this a resonant chain, and it's one of the most elegant solutions to the puzzle of multi-star stability. Think of it like pushing a child on a swing. Time your push is just right, and the swing goes higher with minimal effort. In this system, the stars' gravitational interactions work the same way, their timed tugs keeping everything in balance. The result, a dance that's lasted millions of years and likely will for millions more. The beauty of this discovery isn't just in its precision, it's in what it reveals about the cosmos. Nature, it seems, has a knack for finding order in complexity. While we often focus on the violent, explosive side of the universe, supernovas, collisions, black holes, here we see a quieter, equally profound truth. Stability can emerge from chaos, and harmony can arise from what should be turmoil. This system also challenges us to rethink how we model stellar dynamics. If 6 stars can align so perfectly, could larger systems, with 7, 8, or even more stars also achieve such grace? Or is this the universe showing off, reminding us that even its most extravagant creations can follow rules we're only beginning to understand? As we wrap up our tour of these strange and wondrous sextuple systems, let's take a moment to marvel at what they teach us. They're not just astronomical oddities, they're cosmic classrooms, revealing the limits of our knowledge and the boundless creativity of the universe. From vampire stars to runaway binaries, from ancient relics to celestial ballets, each discovery pushes the boundaries of what we thought possible, and who knows what else is out there waiting to be found. Perhaps the next time we peer into the night sky, we'll spot another sextuple system, one that holds the key to unlocking even deeper mysteries. Until then, the dance continues, a silent reminder that the universe is far stranger and far more beautiful than we ever imagined. Now, as we come to the end of our journey through these mind-bending cosmic marvels, let's take one last look at the incredible oddities we've uncovered. Sextuple star systems aren't just rare, they're cosmic laboratories, constantly rewriting the rules of astrophysics. From the vampire star draining its siblings to the runaway binary pair escaping its family, from the pulsar keeping perfect time in a 6-star chaos to the ancient system older than our own Milky Way, each discovery shatters our expectations of how stars can behave. What's truly remarkable is how these systems force us to rethink everything: gravity, stellar evolution, even our understanding of time itself gets turned upside down when 6 stars share the same space. Take that resonant dance we just marveled at. Mathematicians once swore such stability was impossible in a system so crowded. Yet there it is, defying every model, proving the universe still holds surprises we can't even imagine. And that's the real magic here. Every time we point our telescopes at these stellar families, they teach us something new. Maybe it's a planet surviving in a gravitational maelstrom, or a dark object hiding in plain sight, warping orbits without a single glimmer of light. These aren't just curiosities, they're clues, hinting at deeper laws of physics we've yet to uncover. So here's a question for you. What do you think we'll find next? Another sextuple system with even wilder quirks? A 7 or 8 star arrangement that makes these look simple? The universe has already shown us it's far stranger than fiction, so who's to say what's waiting in the darkness between the stars? Before you go, I'd love to hear your thoughts. Which of these discoveries stunned you the most? Do you think we'll ever find a limit to how complex star systems can get? Drop your theories in the comments. I read every single one. And if you've enjoyed this cosmic adventure, don't forget to hit that like button, subscribe for more deep dives into space's greatest mysteries, and ring the bell so you never miss an upload. The universe is full of wonders, and we've only scratched the surface. Until next time, keep looking up, because out there among the stars, the next great mystery is already unfolding.